Alright, let's talk a little bit about waves. This is going to assume that you've watched the review video from Concepts and remember all of that. So if you haven't done that, pause this, go to the other one, watch it, so that you know everything about wavelength, frequency, period, what a wave looks like, all that jazz. We're getting into kind of details here. Alright, assuming you've done that. Let's talk first about kind of classifications of a wave. Ignoring for a second what's generating your wave, there are two broad categories, a transverse wave or a longitudinal wave. In a transverse wave, the medium moves perpendicular to the wavefront. So you can think for a second if you know any examples of this, and shockingly you do, or should, or at least could convince yourself after the fact. Basic examples of this would be the wave. The wave moves left to right, your hands move up and down. Water wave. Again, water moves up and down, wave moves in to out of shore. And light is going to be a transverse wave. Although we're never really going to get into electromagnetic fields to justify that, but lo and behold, electromagnetic fields oscillate X and Y, light propagates in Z. Now, a longitudinal wave is going to have the medium moving, moves in the direction of the wavefront. The biggest example of this that you've ever heard of is sound. Sound waves, pressure waves. You push sound out, it creates kind of a pattern of high pressure and low pressure. That high pressure, low pressure hits and vibrates your ear, which your brain then says, oh, words. Also, a slinky wave, if you have pushed it. You wobble a slinky up and down, as you can see my hand doing, except you can't see my hand doing that. That's going to be a transverse wave. You wobble up, down, slinky goes forward. If, however, you push a slinky and you get that kind of bunched up thing that like pushes all the way down and just kind of stays there and wiggles, not wiggles, doesn't really wiggle, migrates, that is a longitudinal wave. The wave is that pressure area, that dense part of slinky that moves down the slinky in the direction of that compression. Useful definitions. The thing is, though, you can model either of them in terms of kind of a sinusoidal wavefront. The trick is, when you take a picture of a transverse wave, it looks like a sinusoidal wavefront. When you take a picture of a longitudinal wave, it doesn't. But then if you were to graph the pressure in that wave, or the spacing in that wave, that would look sinusoidal, or could look sinusoidal-ish. Now, if we were to actually do this, this is our basic kind of way of describing a waveform. So y of xt is our height, or our pressure, or whatever the waveform is. It is a function of both position and time. And this is kind of one of those cases where multivariable calculus begins to sneak in. We're not going to end up doing much calculus on this, but the wave equation is one of the first kind of multivariable things that you get into. I could have sworn that I had just written stuff. That's awkward. Try to put this back there for a second. That was y. And I believe I said something to the effect of this being, yeah, whatever. You can remember and scroll back. Alright. Let's look at the parts of this. As we look, a couple of things are going to stick out to us. There are kind of three main pieces of this puzzle. The amplitude, which we know, and then these two crazy things, k and omega. Not a w, that's an omega. We are going to skip talking about k, which is the wave vector, and omega, which is the angular frequency, in favor of looking at lambda and t, our wavelength and period. Now, this is going to get a little confusing. This entire term is called the phase of the wave. Basically, it's saying where you are in the wave cycle. You know, if the phase is equal to 0, you're at the start of a sine wave. So right here, this point, the phase, which incidentally is usually given as phi, is equal to 0. Here, the phase is pi over 2. Here, 3 pi over 2. Alright? Now the idea is that As you advance in the wave, the phase will change, depend both on time. So at a fixed place, as time goes on, the phase of that position will change. It'll move through this wavefront. And at a fixed time, as you move through X, the phase will change. So if you're looking at a snapshot of a wave, you can see illustrated out different parts of different places at different phases. What we want to take away from this, though, is, if we look just at this chunk for a second, it says that, I really wish I knew why that was happening. That was a T over big T. And everything that disappeared over to the left, you're going to have to just learn to live without that, I'm afraid. I'm not repeating it. This says, as X advances by lambda, the phase advances by 2 pi. So we know that the sine function is 2 pi periodic. It repeats its argument every 2 pi. So all this is doing is basically a unit conversion. It's converting from position along my wavefront to a radian argument of the sine function. So it's saying lambda is 1 cycle of this in terms of the position. So if I go ahead lambda meters, I'm going to advance the argument of sine by 2 pi. I'm going to start over my cycle again. Same deal with t and t here. As I advance the time by big T seconds, I bring the cycle right back to the beginning. Alright, we're not going to get too hung up with the algebraic representation of this, but it's important to kind of understand that there is a mathematical underpinning here and that it will, impact us to some lesser or greater degree as we go on. Alright, continuing our jump around. So, one big aspect of this is this idea of superposition and interference. Superposition is not like, delta X putting on some, cape and tights and being all up, up, and away. Yeah, no, it's not that. It's very much not that. Superposition basically says that, if 2 waves meet, they add algebraically. I think this is actually literally what your book says superposition is. Interference is then the result of superposition. Is what happens if I got, on some kind of string or axis or something, I've got a red wave, which is going to look all sawtoothy like this. P.S. Not all waves are sinusoidal, but they are pretty much all periodic. And I've got some blue wave that looks all sawtoothy. Well, that's not really what I wanted to do. Looks all sawtoothy like this. Imagine these are actually crossing at the same point. Pretend, if you will, these are actually mirror images of each other. Oof. Most of those are some vague form of mirror image. This is kind of struggling here. Let's try to help that out a bit. Alright, so imagine that was happening. If I were to take this and add it to this, I would just get 0. At every point, I am as high up as I am below there. So the superposition of these waves would just be one big fat nothing running right down the middle. That is what we would call destructive interference. These 2 waves have arrived out of phase, so they are entirely out of phase. This is at its max when this is at its min, and so they interfere destructively. Similarly, you could imagine constructive interference. If I have, a red wave like this, I hope that's red, and a blue wave that is pretty much the same shape, then my dark green wave will be twice as big. Constructive interference. The basic idea, though, the shape is going to be just added up. It holds for any waves on a string, on a whatever. They do not interfere with each other, so the motion of one wave past the other doesn't do anything to either of the waves, other than the resultant displacement of the medium, which is the sum of them. Lastly, we get to this idea of standing waves. So standing wave, the most common example of this is a string instrument. A string instrument produces a sound by having a standing wave. You have a wave that is traveling on a string, on air, on whatever, and stays there in such a way that there are fixed points on it. And we have labels for these. So, we look, these points that are fixed to be of 0 amplitude are going to be called nodes. These points that are of maximal amplitude are antinodes. It's very creative naming. And basically what happens is that this is going to oscillate with this shape between these kind of two extremes. So this point will go down to here and then back up to there as time goes on. And that will be kind of how it's going to oscillate. Again, this idea of oscillation always pretty much tied into that. Now, the reason we bring this up is because there are very specific types of standing waves. This winds up being a very important aspect of quantum mechanics, actually, basically. So when we look at this, the first wave that can fit on a string basically of length L like this is this waveform. So this is going to be the fundamental or first harmonic. And so there's a specific wavelength that does this. Right now, this part of the waveform basically indicates that the wavelength is going to be 2 times L, where L is this distance. Right? Because this is half of my wave, and half of my wave took a distance L, so the whole wave will take a distance 2L. The next harmonic, the next shape that will fit here, is going to have one more node. Right? This has 2 nodes. This has 3 nodes. And now the wavelength of this is equal to L. This is the second harmonic. And then so on and so forth. We can get to a third harmonic. Gonna add one more, nope. Gonna add one more node. Now it gets a little tricky, right? So the wavelength is 2/3 of L. Yes. That sounds right. 2L over 3, right? Because here is one wavelength, and I can fit another half of a wavelength onto that. I'm hoping I did this right. Someone will catch it. Someone will catch me later if I'm making crazy things up. Alright. There are formulas you can memorize about this, but realistically you very rarely have to know the nth degree, the nth harmonic, or whatever. This basically has, it's going to dictate based on the size of the string or the size of the opening what pitch you will produce on an instrument. So it's a neat little thing. We'll play with it a little bit in class. All right. So hopefully this gives you a solid overview of everything. Descriptive types of waves, algebraic description of waves, this idea of superposition and interference. Goodness, I wish I knew why things were disappearing. And again, this idea of standing waves. We're not doing too much of this in a algebraic numerical sense. So you really just want to try to get a good grasp of these relationships graphically and how they a sense of how to play with them.